Today we're going to talk about Taylor polynomials, right? So think back to first year, Math 1, 2, 3, 1. Let's go further back. Let's go further back than that. Let's go way back to school. Okay? We were told something. See if you remember. At school, hang on. Might do that a bit more. Is that all right? All right. At school, you were told that the sine of x is approximately equal to x. Does anybody remember that? Right, yeah, a bit vague, right? Is it true? Well, let's have a look. Let's go to GeoGebra for a second. Yeah. All right, so I'll put in sine x. I'll switch this over for those watching at home in a minute. Okay, so obviously the green curve is the sine curve, and the blue curve is the x curve, right? So when we say sine x is approximately equal to x, what are we really talking about there? What are we restricting our attention to? Anyone know? Yeah, down the front. Yeah, so let's zoom in a bit, right? Let's zoom in a bit. Because it doesn't look like it's a very good approximation there, right? So let's move in. Looks a bit better? Yeah? So for these values of x, let's say between -1 and 1, it seems reasonable, right? What happens if we keep zooming in? Okay. There's not much difference between the two graphs, right, on that picture. I've got glasses on, I still can't really tell them apart, right? So when we say that approximation is reasonable, what are we really talking about there? What sort of x conditions are we talking about? So you're saying between -1 and 1. What else can we say?
Values close to 0.
Exactly, right? So -1 to 1's fine, but even better, even more precise, we can say for x small, x close to 0. Yeah? So no, you can keep going in, right? Okay. Now, what else is going on there? The blue line looks like it's tangent to the curve. Okay? And this is a more general thing. We can use tangent lines to approximate crazy functions and crazy graphs. That's the key thing here. Yeah? We can use tangent lines, because tangent lines are simple linear expressions, to approximate nonlinear things. This happens all the time, right? Nonlinear stuff is complicated, linear stuff is much easier to digest. Okay? So going back to our school stuff, this is what we can say. All right, let's do something else. Let's think back to first year, right? What do we know from first year? Okay. Our old friend, e to the x, the exponential function. In Math 1b, you calculated approximations to that. Right? Now, you've probably forgotten them, but it was something like this. Yeah? Anyone remember that sort of crazy expression or nightmares? Yeah? Yeah, 75%. Okay, good. So if I actually cut off two of those terms, what have I got left? 1 plus x, right? That's tangent line, right? Linear approximation. Okay, I can put in the x squareds and the x cubes, no worries, but let's just start simple. Okay? So, this is a linear approximation for sine x. That is a linear approximation for e to the x. Let's have a look. No, I don't want to verify my account. For everyone at home. Okay, so you can see the nonlinear part, which just increases exponentially. And you can see the linear part, which is sort of a reddy orange approximation. Can you also see how it's a tangent? Yeah? Okay, and it's a much simpler curve. But again, what happens when we move away from x equals 0? The two graphs split apart, right? So if we use an approximation like 1 plus x, it's okay as long as x isn't too large and positive or too large and negative, okay? All right, so where am I going with this? Well, I'm glad you asked. What happens with the surfaces and the functions of two variables that we were looking at yesterday? Okay? That's the question we're really going to look at today. What happens where it's not a curve, it's a surface, and it's not a tangent line, but what do you think it'll be instead of a tangent line? A plane, yeah.
A plane?
Exactly. Yeah, that's it. Well, you've got to record for the people at home, right? That's why I'm a bit obsessed with the microphone. Yes, it's going to be a plane. And it's going to be a special plane, tangent plane, tangent plane. So what does the tangent plane do? It touched the surface at one point, right? Special point, and it's like another linear expression. Okay, if you can understand that, then that's it. That's basically the whole lecture. A good question though is, how do I calculate these things and how approximate are they? Well, again, I'm glad you asked. Okay, I've got an example here, but before I get to that, let's just look at tangent planes. Okay. Just give me a sec. All right, so these are your nonlinear terms, at least for e to the x. These are your they're called higher order. Okay, and the more terms we have, the better the approximation is, but it involves more computing, right? Okay, so let me just... All right. So let me show you the way to work out these approximations for functions of two variables. All right, here it is. Multivariable Taylor series. Okay, so in first year, you would have used the words like series, Taylor series, Maclaurin series. We can just use Taylor series as a general thing. Okay, so what is going on here? you've got a function of two variables. And you know its value at a point. And then you've got some linear parts, right? So you've got x minus the number and a derivative at the point, y minus the number times the derivative, okay? So that's the plane that you were talking about before, right? That's going to be the tangent plane. Now, if we take in more terms, we get more and better approximations. So these terms here, it's a huge mess, right? Like that is a mess. They're called the quadratic terms. Why? Because they involve squares, basically. Okay? So on the top line, you've got the linear approximation. If you add these quadratic terms to it, you get a more precise approximation, but you don't get a plane, you'll get something else. Okay? Now, this is all based on the Taylor series and whatnot that you saw in first year. Okay? The only difference is it involved partial derivatives, including the second partial derivatives. Okay? Now, let's just have a look at those second partial derivatives for a second. Okay? So basically with that one, you're differentiating the original function twice and subbing in AB with respect to x. Same over here. What about this one? Okay, what about that one? It's the mixed one. Does it matter which way I do it? Like in this case, I've done the y first, differentiated with respect to y and then x. Does it matter? No. Usually it doesn't matter. There are some crazy cases where it does matter, but for these sort of functions, it doesn't really matter. Okay? All right, so one of the questions on your class test, Mobius weekly quiz this week involves computing the coefficients and the form of this, okay? So why don't we just have a look at a simple example and we can go through it. All right, so let me see if I can put this document camera on projector one. Yeah, that'll work. Okay, so before I do that, let me do a real simple one. Okay, suppose I have this. No, I won't do that. Hang on, I'll change that a bit. Okay. Function of two variables. Let's go and see what it looks like. Okay, so for everyone at home. Not bad, huh? Okay. And let's just see if we can apply these ideas to form an approximation for this at near 0, 0. Okay. All right, so let's just go through it super simple, and it's just basically an exercise in computation with partial derivatives. All right, so we'll approximate okay? All right, so with these sort of problems, what do we need? We need the value of the function and its derivatives at the point of interest. So essentially, you just form a list. All right, so that's going to be 0. So by this notation, I'm talking about the partial derivative with respect to x evaluated at 0, 0. So what's the derivative here with respect to x? Who can tell me? Sine. So I'm going to get 0. Okay, not very exciting. Okay, what's the derivative with respect to y going to be? Who can tell me? Come on, it's not a... Yeah. X cos y, exactly. So we imagine x is a constant and we differentiate with respect to y. So we're going to get 0 again. Okay, we got 3 zeros. So let's do the second order partials now. Okay, so we differentiate with respect to x and we're going to get 0, which of course is 0. Let's do the other ones. Okay, differentiate with respect to y. So we're going to get negative sign, right? So that's also zeros. Oh my God, we're getting a lot of zeros. Let's do one more, the mixed. Okay, so I'll go up here, I'll differentiate, I'll get cosine equals 1. Oh, thank God, something that's non-zero. Okay? All right, so now the challenge is to put everything together with the big mess. Okay? Now, luckily, we've got plenty of zeros there, so we're only going to get one term that is not 0. Okay? So all of these are going to give us non-zero except for this one. Right? Okay, so if we simplify that, the half and the 2 is going to cancel. This is just 1. We're going to get xy. Whoop, you go up. Okay. All right, so let's see how good that is. Let's see how good that is. Okay. Ooh. So if you have a look on the GeoGebra picture, the pinky purple curve is the original one, and the black one is our approximation. It looks pretty good, right? As long as you're close to x equals 0, y equals 0, it's quite hard to tell the difference. But if I zoom out, right? If I zoom out, you can see, say over here, there's quite a bit of difference between the two surfaces, right? Now, is that a tangent plane? No. Right? We could have formed a tangent plane. It would have just been horizontal, right? So that would have been okay, but not as good as this. Questions? Questions. Now, will you get the formula for these crazy series? Yes. You don't have to write it on your hand or anything. It's fine. Right? Even in the lab test, you'll get it. Okay? So it's less remembering, more, I guess, constructing or computing. Questions? So you don't need to remember the formula, you just need to get good at computing partial derivatives. Okay? But yes. Oh, what? Oh no, did you have one? No? Okay, hang on. I notice there's 2 extra mics here. If I can get them working, I'll distribute, okay?
I don't quite understand how you got to like the last line, the x sine y is approximate to. Is that from the other page where you went to the big Taylor polynomial?
Yeah. So let me show you. So that's a good question. So this is our original function. And that's what we're trying to approximate. Okay? So if I go back here, that's it. Okay? Right? And you can, what do the dots here mean? That's also a good question. It means that the terms just keep going. We can't compute all the terms. Right? So we're just cutting it off and we're saying, hey, that's our approximation. Right? That's our approximation. Does that make a bit more sense? Okay, thank you. More questions? Okay. All right, so not difficult. There's one in this week's class test. Sorry, not class test, a Mobius quiz, right? Let me show that to you. Is it that one? No. That one. Okay. So let me put that on for everyone at home. So this is a bit of a weird question actually, because they're giving you a polynomial and you're supposed to approximate it using a different polynomial. Mind blown, right? Like x times y to the 4th, that's a polynomial in 2 variables. You're like, oh, polynomial, what's that? I thought I left that with algebra last year, right? So it's like, I got to say, when I saw this question, I don't write the questions. When I saw this question, I was like, okay, that's a bit weird. But you can do it, okay? You can do it. So, and also in this question, instead of being at the point 0, 0, you can move around, right? So you can be at x equals 2, y equals 1, and then you just shift these things, right? Just shift them. And these things are just the derivatives at the point. Okay? So it's not like super difficult. You just need to make sure you don't make a mistake. I know I did it. I made a couple of mistakes when I was computing it.
In this question, the coefficients wouldn't be affected by which point you select, or would they be?
Yeah, good question. So let's say we were at the point 0, 0 instead of 2, 1, right? Differentiate f, or actually just put in 0, 0 into f. What do you get? You don't get 2, you get 0. So the coefficients are sensitive to the point. Yeah, good question. Okay, so yeah, so the formula incorporates, you know, the AB point. AB could be anything, right? 0, 0, 1, 2, 2, 1, whatever. Okay, you just need to manage it. Yeah. Other questions? Yep. Hi.
I have a question about the last question you just did. Like, how did you like get half and 2 in the last step?
Okay, so where did the half come from? Yeah. Okay. Oh, I've got to go back now. So many Mobius tests, so many. All right, now, can you see the 2 down there? 2 factorial is just 2, right? And you've got the 2 there, because when you compute these derivatives, they're sort of, they can go both ways, right? And so you're sort of adding 2 of them together, if that makes sense, yeah? So it's a bit weird. Why would you have a 2 here and then a 2 down here? Anybody know why people do that? Seems a bit weird. Anyone know? Any theories? Because, you know, you see it in the original series from first year. So that's 1 factorial, that's 0 factorial, right? So they're trying to preserve that form, if that makes sense. Yeah. Great question. All right, so let's do a question from today's sheet. You can use Taylor polynomials, Taylor expansions to approximate functions and values. So this is a very common kind of question for this course. Use an appropriate Taylor polynomial, compute an approximation to this mess, okay? So what we're trying to do is use a tangent plane, at least in this case, to approximate some highly nonlinear function that is not so easy to work with. All right, before we do anything, let's actually stand back and think about what this is approximately equal to. Okay? So it's the square root of 1.02 cubed plus 1.97 cubed. What is that almost? 3. Exactly, right? Because the first term is about 1. The second term is about 8. Add them and take the square root 3. So when you're doing your answer, if you don't get something that's close to 3, right, that's the problem. Okay, so that's like the sense check. It's going to be close to 3. How close? Well, let's see how close we can get. Okay? All right. So the way I usually start these problems is I look at, first of all, do the sense check, and then I form a function. And it's based on this, x cubed plus y cubed. Okay? And what I'm going to do there is say, okay, 1.02 is close to 1, 1.97 is close to 2. Let's work with that. Okay? So this and this are the same. All right, what does our expansion say? Okay? So what we've got here basically is we've used a tangent plane on the right-hand side instead of that crazy function, and we've subbed in the values. So all we need to do is compute the partial derivatives and evaluate them at 1, 2. Now, I'm sure you'll agree, x equals 1, y equals 2 is much easier to deal with than, say, 1.02 or 1.97. Okay? So this is the tangent plane or the linear approximation. Okay, so let's compute these derivatives. All right, so we are differentiating this with respect to x. One way to do it is to write the square root as a half and differentiate. Okay, then you plug in, oh, sorry, 1, 2. And then plug in x equals 1, y equals 2. Okay, so what's going to happen when we differentiate this mess here? Well, the half's going to come to the front, the 3x squared is going to come to the front, and you decrease the power by 1. Okay? I'm assuming you're okay with partial differentiation, but just in case you're not, let me say that again. Okay? If I'm differentiating with respect to x, I imagine all the y's are constants. The half will come to the front, the derivative of what's in there will come to the front, 3x squared, and the power will decrease by 1. Okay? So so that's the derivative, and I'm substituting in x equals 1, y equals 2. Okay? If I do that, I get a half. Now let's do it again, okay? Differentiate this with respect to y. So imagine x is fixed, just differentiate normally with respect to y. The half comes to the front, the derivative of that comes to the front, and you decrease the power by 1. Okay? So when you plug in x equals 1, y equals 2, you'll get 2. Just need to be a bit careful with that. Now remember, if you're doing something like this in Mobius, Mobius also acts like a calculator sometimes, where you don't have to simplify things before you input them. Okay, it can't differentiate, it can't integrate, but it can do simple arithmetic. Okay? All right, so we've got our 2 bits, let's put them together, and then we'll have our approximation. Okay, that's going to be 0.2, that's going to be negative 0.3. So writing those as fractions. F of 1, let's work out f of 1 too. Okay, so that's going to be 3. Okay, so that's that term. This term is going to be a half times say 2 100ths. And then here we're going to get 2 times negative 3 100ths. Okay, so you can write it as a decimal if you want. Sometimes Mobius will ask you to round something to like 2 decimal places. Again, you can use Mobius as a calculator and then just round it yourself. So how close did we get with our approximation? This is like 2.95. So let me put that into Mobius and see what happens. I just want the calculator. Okay. Okay. All right, the big reveal. So you can see up the top left-hand corner, 2.95069616, blah, 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 blah. So 2.95 sounds okay. I mean, it's just a linear tangent plane, right? Like you can't expect too much. You can't expect too much, but that's pretty good. Right, you can work out what the error is and all that sort of stuff. Questions? Yep, hang on, I'll get to you. So when you're given these problems, the first thing you have to understand is, do I want a tangent plane or do I want something more? Do I want quadratic or the squared terms, things like this? Oh, making me work hard.
Yes, my question was, when do we know when we need the tangent plane versus the quadratic?
Yeah, good question. So the instructions will usually tell you, right? So on this week's class, the weekly Mobius quiz, it was clear that they wanted the quadratic squared terms, right? But they can say, you know, linear approximation, tangent plane, those sorts of terms mean you don't need the squares. Right, the squared terms. So I think just read it carefully, right? Oh yeah, so here, yeah, so, okay, so you're saying that's not in there, right? So I've chosen to use an appropriate Taylor polynomial just as a linear approximation. I've chosen it. But usually the question will say, hey, use this or use this, okay? Yeah, probably I should have been clearer there. But it was I think I did the YouTube video for this like 16 years ago or something, so I knew less then. I knew less then. More questions? Okay. All right, so here's the Taylor polynomial up to and including linear terms, unless a greater degree of accuracy is required. Okay, so what does that greater degree of accuracy involve? So it would be something like this. So if I wanted the quadratic terms in there, it would be something like this. So it's all of this plus some extra terms. Yeah, and then the mess. Okay, now you don't need to remember it, it'll be given to you. It's pretty easy to compute, but so how do people make mistakes on these sort of questions? they just are careless, they make a substitution error, or they make a syntax error, or they make a, you know, some silly mistake. Okay? Any more questions? All right, let's take a break. We'll come back at 5 past. If you have any questions, come on down. Have a chat. Okay, everyone, let's get back to it. All right. So there were some very good questions during the break. So the most popular question was, just tell me what to do. Do I use this one or this one? Right? The question, well, sometimes you can choose what you want to use, right? But most of the time the question will say something. It'll say, use a linear approximation for this. That's the tangent plane up the top. Sometimes the question will say, use a Taylor approximation up to and including quadratic terms. That's the bottom bit. Okay? Other question was, what is that? It looks a bit sick. So I quite like smiley faces, and this is how a lot of mathematicians would finish like a theorem or a proof or a paper or whatever. It's called a tombstone, right? It's a bit sort of dark, but that's the name for it. So yeah, so you put them together, you get, I don't know, a smiley tombstone or something. I don't know. Anyway. All right. So in this second lecture, we're going to look at error estimation. And again, it's very similar to the questions we asked earlier this morning. We've seen something in first year maths. Can we look at it with surfaces and functions of two variables and all this sort of stuff? Okay, so there's kind of an analogue of that in this lecture. All right. Okay, so let's just refresh our memory with a little bit of first year. Suppose you've got a function, right? Just a function of one variable. Okay? And you take a measurement in, say, the x, the input, right? But you're not sure about it. Okay? So you might be measuring something or estimating something. That goes into a calculation for something else. Right? So the example I'm going to look at today is the volume of a can, right? What do you need to get the volume of a can? You need the radius of the base and you need the height, yeah? But what happens if you can't measure those two things very accurately? Okay? How bad is it going to be? Okay? So for functions of one variable, you would have looked at something like this. Okay? Now, the x is the thing that you measure or you estimate, right? But you're not 100% sure that it's entirely accurate and correct. The delta x there is like the error in your measurement. Okay? So you can think of that expression up the top as being the difference between what you compute here and what the actual true value is here. Okay? So what do we know about that? We can, at least, maybe you even saw it at school. You can come up with a way of estimating the difference between the true value and your computed value, okay? So the inequality means it's like an estimate, maybe equal, but it probably won't be. And it involves tangent lines, right? So what do you think we're going to do today if we're working with surfaces in 2 dimensions? We're going to use tangent planes, right? You're not going to have one input or one measurement, you're going to have 2. Okay? Which both may have errors in them. What is the knock-on effect? What is the consequence of those errors in your estimation, in your final output? Okay? So instead of using the regular derivative, we'll use partial derivatives. Instead of using a tangent line, we'll use a tangent plane. Okay? So we're just going up 1 dimension. Okay, so I guess I can read this. This is no problem. So when we take measurements, we do make errors, right? So what we turn to is, okay, well, I can maybe estimate that to a certain degree of accuracy. Is that okay? And what are the effects of small variations? Okay? That's the idea. This is very common. Okay? All right, let's have a look at our example. Okay? So we've got a can that's a cylinder. It has height h and radius r. So what I like to do with these ones is I like to draw a little picture, even though I'm quite bad at drawing pictures. I remember having a meeting with one of my colleagues when I was younger. He said, "You can't draw." I'm like, "I know." Okay, so we've got the height, we've got the radius. Okay, all right, so when we do our measurements, at least in this problem, we estimate the height to be 12 centimetres, and we estimate the radius to be 5 centimetres. But they're not. There may be errors in those. Okay, we're told that the tolerances that we have with the errors are no more than 0.5 millimetre. Obtain an estimate on the percentage error in calculating the volume of a can. So you're measuring something. You know it's not going to be entirely accurate with your measurements. You use those measurements anyway, and you see what happens. Okay, you can come up with an estimate on how bad it's going to be or how accurate it's going to be. Okay, this is a classic Math 2019 example. You see these a lot. Okay, might not be a can, it might be something else, right? Something that involves 2 things. All right, so let's work it out. So let's let the volume be V. And it's going to be pi r squared h. So 2 variables there. One is the radius, one is the height. Now, what else do we have? Well, we measure our height to be 12 centimetres plus some error. Okay, and the radius is going to be 5 centimetres plus some error. Okay, so the way I'm going to denote this is going to be h naught, r naught's going to be 5, and then our estimate is this. So it's, what is it? It's less than 0.5 of a millimetre, right? So it's going to be, I'll just put it all in centimetres. Okay? So, how can we use the tangent plane here to help us out? All right, well, let's have a look. it's going to be very similar to what you have here. Instead of this, we're going to have a partial derivative there times delta h, and then partial derivative times delta r. Okay? So let's do some calculations. So I'm going to let the error in V be, so this. Okay, so this is your V of H and R. All right. So that'll give me something in cubic centimetres, but remember I want to get an estimate of the percentage error. Okay, so I'll come back to this in a minute. All right, so using the tangent plane, I can do this. So I'm going to expand that so the minus will go to a plus. This is multiplication. Okay? So basically I've just used a tangent plane there, and I've put absolute values, and then I've formed an inequality using a triangle inequality. Okay? Now, will you get this in your class tests? No. No, but you can get it from the Taylor series, the linear approximation. You just need to move things around. Okay? All right, so let's work this out. Right, H0 is 12, R0 is 5, and these are the estimates on our errors. Okay? So I'm going to say pi times 5 squared times 12 times 0.005. Okay, so I've basically just gone up to my formula and put in R0 equals 5, H0 equals 12. And, oh, hang on. I haven't differentiated there. Hang on, I need to differentiate. So V sub H is going to be pi R squared, right? V sub R is going to be 2 pi RH. Yep. So, did I do that correctly? Yeah, I shouldn't have had that 12 in there. Okay, so that's going in there. And this one's going to be 2 pi times 5 times 12. And now it's just a game of simplifying it. Now remember, Mobius can simplify these expressions. Okay? So if, I'm going to write it as a fraction, but even in this form, right? You get something like this. Okay, I haven't simplified it. At the moment I don't care. So that gives you an estimate on the error. But they're asking us in the bottom line for an estimate on the percentage error. So it seems like we would take this error, divide it by the volume and multiply by 100. All right? So now we can go back up here and say, hey, with my original H0 and R0, let's put them in here and we'll get something. All right, so they were my calculations. So we've non-dimensionalized it. Our answer is a percentage estimate. Is it okay? So let's just think about the answer for a second. Right? Let's just think about what we've actually calculated. Our errors were pretty small. Right? So one measurement was 5 centimeters, the other one was 12. And the errors were less than half a millimeter, right? That's pretty small. That's pretty small. So is 2.5%, is that okay? As a sort of percentage error? Is it okay? Does it sound large to you, or does it sound okay? You're not sure, right? You're not sure what the expectations are, I guess.
It feels a bit small.
Yeah, okay. 2.5% error. I just would have thought, you know, these things are, the errors are half a millimeter. And you're coming up with 12 and, 12 and 5. I thought it was, I was a bit stunned when I saw that, actually. But what else is at play here? What happens if, for example, what happens if I switched my measurements? Let's say I measured the height to be 12 and the radius, the height to be 5 and the radius to be 12. So we're flipping now. It makes a difference, right? Yeah.
It's because the radius is squared, right? So its error is compounded in that regard.
Yeah. So obviously the function that we're working on plays a huge role here, because if you change the inputs, it's going to have a big output. And you're right, because of the squared, that's going to, like you say, compound whatever rough estimates we put into it. Yeah? Okay, questions? This, I got to say, this is a last time I taught this course was 13 years ago, right? I remember this question. This is a classic Math 2019 question, okay? So I think it's interesting. You've probably seen stuff like this before, but I think it's super interesting, especially because we're using tangent planes, basically, right? We're using tangent planes. More questions? Okay. Let's... Yep. Let me just open up a Mobius question. Yeah. No, 2024, it's last year. Oh, yeah. Okay, so for those of you who haven't seen it, this is something that is in this week's quiz, right? All right. So let's read the question. Some of you may have already done it. You know, you got deep seek onto it, or what was the old Chinese one? Was it Ask Eric? Ask Eric. I think that was before DeepSeek. You can see in the first sentence they tell you exactly whether you want linear or quadratic approximation here, right? The first three terms, yeah? So that's linear. Yeah. Use the first three terms of the Taylor series. For this function, about this point, what's the function? We don't know. It doesn't matter in these sort of questions. It doesn't matter what the function is. Okay? What's A and B? Well, A is going to be 25, B is going to be 24, and then they talk about the maximum absolute error of 0.05 in X and maximum absolute error 0.03 in Y. Okay? They even give you the approximative formula, which is nice. You can't get much better than this, right? Again, I didn't set the question, but okay. So if I was doing this in Maple, you can see I've already completed it. But what would I be doing here? I would be saying, okay, let's form an inequality on this, right? And basically you're using those inequalities there. Okay, so if I was doing this, what I would do, I would say, right, that's going to become less than 0.05, that's going to become less than 0.03, and you just multiply by these terms and this will go to plus. Okay, so let's try it. Plus over 7. Okay, so see how it's computed it? Okay, right? But if you put that in, it's wrong. Why is it wrong if I do that? Should we? Yeah, 2 decimal places. So I go here. I go. Oh, okay. That's gonna become 0. So it'll be 0.28. Let's just try it. How did I do? No! Okay, maybe I've made a mistake this morning. I was up very early trying to prepare for this class, you know, especially after yesterday. It's the timetable for this course. Whoever did the timetable, like 4 to 6 and then 9 to 11 the next day. That's rough. All right, so maybe there are situations where you don't have to round it. I wonder how it decides. Yeah. So either if you put in the exact value, it's fine. But should we just put in 0.28 and see what happens? Okay. Oh. I don't know. I don't set the tests. So, is that a good thing or a bad thing? Should I be reporting this to Central IT or no? It's okay. All right. Diversity. Embrace it. I like it. So you can see this is a pretty easy question, right? You don't even have to use pen and paper. You just if you can just type it in, it'll compute it. Questions? Okay, well, let's go back to our previous example. Let's talk about if we switch our inputs. Let's see what happens. But let's just summarize everything first. So the main inequality that we used can be derived from the Taylor polynomial or the linear approximation, whatever you want to call it. Unifying the units is important. That's another mistake a lot of students make. So you want to have all centimetres or all metres or all millimetres or whatever. Just you want to be on the same page. Okay? And so the inequality is something like this. Oops. Okay, so there's no f there. This is just one function. So that's your error. The thing on the left is the true value, and the thing on the right is your approximative value. Okay? And so this is going to be less than sort of squished it in. Okay? All right, so what happens if we switch up the measurements in the previous example? That's what they're talking about here. So, you know, instead of having the height be 12 and the radius be 5, you've now got about 12, sorry. No. Okay, what happens with that? Is that better or worse? So let's find out. Right? So if you do your calculations, you get something like this. Let me fold this on. See if I can squish it in. Okay, so we end up with this as our estimate for a percentage error. So it's less than 2%. Okay? So it's less than 2%. The other estimate was about 2.5%. Okay? It's less than 2%. So the measurements matter. They're the inputs. And of course the function that you're dealing with matters. Right? Questions? Sorry, my writing's very messy. I try to write as neat as I can.
This is a question regarding the calculation of the fractional uncertainties. So I think in certain science courses, we were told that when you are multiplying measurements together, you add their fractional uncertainties. And when you added them together, you would add the absolute uncertainties. I checked this particular case against, like I tried to do the same technique and then that technique, and it returned the same values for this question, would it also return the same values for other questions?
Good question. Let me give you another one to do. Try with your method. Try this one. Can you try it? It's not super hard, but certainly there are more methods. Like, I'm just trying to show you what you can do with the tangent plane and partial derivatives, right? If you're going, no, I'm going to fight the power, I'm going to use my other method, that's okay. I don't mind that. Like, one thing I hate, people who had me last year, or maybe you remember this, one thing I hate is when you get a question on a test and it says, use this method to solve this problem. And you don't know how to use that method, but you know a different method. But you lose marks because you didn't follow the instructions, right? Why can't you use a different method? You should be able to, right? You should be able to use as many methods as you want. So one thing that I'm very sympathetic to is other methods, okay? Let's go back to diversity. If you have a better method, a faster method, a more comfortable method, use it, right? I don't want to mark you down for not following my instructions, right? Does that make sense? So you should be able to use any method you want. I mean, if it was up to me, Maple's not a part of this course, but maybe it should be, right? Like, why shouldn't you use computation? But even like AI, why shouldn't you use AI? It's less about the computation, right? It's more about the interpretation. So AI is saying this, Maple's telling me this. What does it mean? Is it true? Is it wrong? Right? So I actually think we're going to move away from computation, and it's more about validation or interpretation. That's what I think. Anyway, anybody study computer science here? I know there's no comp sci majors here, right? You do? Can you bring back single sign-on? Can you bring it back? Like, the number of times I have to log in and get my phone out and put my thumb on my phone and, like, people in IT, but a long time ago I worked in like management here. I was a associate dean, and I used to have these crazy meetings with people up the hill, and they would talk about seamless integration, right? Of the web experience and digital, digital wayfaring and all this sort of stuff, right? Man, if I have to do 5 things to log on to Moodle, that's like, I'm upset. Just stop it. So yeah, if you bring it back, like, that would be great. Yeah. Even things like a document camera, right? This thing at the front's called a document camera, and they're great. They're a little bit old school, but I love them, right? Even just plugging in some hardware into my UNSW machine, it blocks pretty much like every driver now, right? So I took my camera to the IT and I said, oh look, my SOE machine blocks the driver. I can't use it in lectures. And they go, we will have to run this through our cyber security team. I'm like, what? And they're like, we don't want to end up on the front page of the Sydney Morning Herald. I'm like, what universe do you live in? Like, I was thinking this, I didn't say this though. I said, look, you could end up on there for not doing this. Let me just tell you. Anyway, rant over. Now, another good question here is, will you see these kinds of questions on the first lab test? And I did do a bit of searching. From last year's questions. Let me put that on both just for everybody at home. Okay, lab test 1, all questions. Okay, everybody get your cameras out. All right, now, we will go through this later, right? Partial derivative, partial derivative, partial derivative, chain rule, chain rule, chain rule, chain rule, chain rule, chain, oh, partial derivative, something else. Now, I don't see any Taylor polynomial questions. Okay? I couldn't see any. Oh, hang on, what was that? Oh, it's plain. No, that's an optimization type of thing. Yeah, so I'm just going to fess up. I don't think there are any questions on this in the lab tests. Okay, so you'll probably just do it this week and then maybe forget about it until the final exam. All right, more questions? Question? No? All right, I think that's all I have today. If people have extra questions, come on down. And I appreciate you being here at 9 a.m. in the morning. Tomorrow, you know what the time is tomorrow? Friday afternoon, 2 till 4. So, you know, only the strong will survive that. I'll see you tomorrow, but please come down. There's like 10 or so minutes for consultation. So, and have a great day.